Yeah, I welcome you all to the last and the final live interaction session of this course, Introduction to Rings and Fields. So it's Harish. I am a student at ISR Mohali, and today we are going to discuss assignment number 8. And then, if time permits, then we will finish the one remaining question of assignment 7 that we could not discuss last time. And if still some time left, then we will go to assignment number 6. Yes. So uh, let's start. I hope my screen is visible and my sound is clear. If not, then you can just interrupt me in between and ask me to improve it. Okay. So it's Session-8. It's 24. And we are going to discuss assignment. Okay. Let me just paste question number 1. Yeah. So it says choose all the correct statements. Uh, Q and C are in the usual notations, denote the field of rational numbers and the field of complex numbers. Uh, so the first option says if K and F are field extensions of Q and phi from Q to F is a field homomorphism, then phi of R is equal to R for every R in Q. So for any field extension of Q, uh, if you are having a field homomorphism, then it will fix each and every element of Q. So this we have already discussed in the previous live interaction sessions also, but just for the sake of revision, let me redo it. So we have, so we are solving part A. Phi from K to Q a field homomorphism. Okay, so this implies that phi of 1 should be equal to 1, right? Because the field homomorphism always fixes the multiplicative identity and the additive identity as well. So phi of 1 is equal to 1, that's okay. Now, if since it's a field homomorphism, also since phi is a field homomorphism, here we can also write phi of 0 is equal to 0. There is no issue with that. So phi is a field homomorphism, therefore what will happen? Where this element will map, phi of n, this is phi of 1 plus 1 plus 1 plus dot 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 1 n many times, right? Where you have n to be any natural number. So this is equal to phi of 1 plus dot 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 phi of 1, since this is a field homomorphism. So it is also compatible with the additive operation. So thus you will have this to be n times, but phi of 1 is what? Phi of 1 is 1. So you have this to be adding 1 n times. So thus this is nothing but n. So what does this gives? This gives that phi of n is equal to n for all n belongs to n. Right? Now, you we all know that phi of A inverse is equal to phi of A inverse. So phi of minus n, which is additive inverse of uh, n, is nothing but phi of minus phi of n. This is minus of n, right? And this is also true for all n belongs to n. Since we already have phi of 0 is equal to 0, thus we got phi of alpha is equal to alpha for all alpha belongs to the set of integers. So it fixes the set of integers, but we are demanding more than whether it fixes q or not. So till now we just have used the additive, the compatibility with the additive operation only, but field homomorphism is also compatible with the multiplicative operation. So let p by q, where q is non-zero, this q is non-zero. Let this is an element of, let this be a rational number. So what will you get? This, just a minute. So let this be a rational number. Then what phi of p by q is? So phi of p by q is nothing. P by q is what? P times q inverse, right? And this is phi of p dot phi of q inverse, and this is nothing but p dot phi of q whole inverse, and this is p dot q inverse, which is nothing but p by q. All this is happening since pq belongs to z and phi is a field homomorphism. So combining all these things, what we actually get, we get that phi of alpha is equal to alpha for all alpha in q. So any field homomorphism from a field extension of q to q fixes a q. Oh, sorry. So here, instead of just saying that we are having a map from q to k to q, we can actually have this map from any field extension k to any other field extension f. So this codomain need not be q, but if it contains q, that's also fine. So you always so each field homomorphism from in between the two field extensions of Q fixes Q. Okay, so the option A is correct. So A is true. Okay, so if that is clear, then we can move to the next part. The B part is B part says if K F are field extension of Q root 2 and phi is a field homomorphism, then phi of alpha equal to alpha for every alpha in Q root 2. So in the first part, we saw that if K and F are field extensions of Q, then it fixes each and every element of Q. But now the second part says if Q and F are field extensions of Q root 2, then it fixes every element of Q root 2 as well. So definitely a field extension of Q root 2 is also a field extension of Q, but so we just need to check that what happens with root 2. Okay, so by part 1, oh sorry, the sharing app just crashed. Let me just reopen it.
Okay, so this is the problem solving session, right?
Yes.
So I have a question. Should I ask it?
Yeah, you can ask. You can ask.
Okay, so in the structural theorem for finite fields, there was, I think, 6 parts. So the
Yes.
part said that there is a field of order Q.
There is.
There is a field of order P to the power R.
Yes.
Where P is prime and R is a natural number.
Yes.
So in the proof, actually, in one step, there was differentiating both sides. This was done, but my question is, what is the meaning of differentiation in this case in arbitrary polynomial ring?
Okay, so maybe if possible, I can share that video if you are comfortable with that.
Yeah, so should I share that video or?
I can share. I can share. So let me first stop sharing this. So do you remember in which lecture it was? I think finite fields. I have 3 lectures, 1, 2, 3. So
yeah, so finite fields 2.
2. Okay. So, it's opening.
It's around 12 minutes, maybe. Let me check.
Okay. Yeah. Can you see the screen?
Yeah, let me see. Let me see. Yes, I can see the screen.
Okay. So let me just try to play it if I can do it from here. It's around.
So probably not 12 minutes. I have to check where it's, yeah, it's somewhere around here.
So you can see the video, right? Might not be able to hear this sound because I have turned it off.
No. I think yeah, I can hear you, but not the video sound. Yeah.
Okay, that's fine.
So yeah, this is the place.
This is the place. So here he's differentiating. So let us just go to the proof once, right? Sorry. Yes, section theory. So this is structural. So you have doubt about the first part.
Yeah, basically the differentiation step. So
So that is part A, right? There exists a field of
yeah,
order
yeah.
Q. Okay. So saying, so we just need to show that there exists some field. So we can choose a field of our own choice, which has very nice properties.
Yeah.
Okay. So for the construction of that, is taking an irreducible polynomial, or that every polynomial or a field has splitting field. So a polynomial in FPX of this form xq minus x, and the splitting field always exists for any polynomial. So
Yeah.
he's then considering the splitting field of this polynomial. So it's just the field where this polynomial splits completely, okay, into linear factors. Then K is alpha belongs to L, such that alpha is a root of xq minus q. So this is just a subset which contains each and every root of this polynomial. So
Yeah.
this subset will, the element of this subset will satisfy this property that alpha raised to q is alpha. So then he is saying we are done if we show that K is a field of order Q. Okay.
Yeah.
It's all about existence. So he is claiming that this field K will be a field of order Q. Okay. Then in the first part, he will show that Q has K has Q many elements. For that, saying that suppose that K has less than Q elements, one root must be a multiple root, because the polynomial xq minus x has q many roots and k is the collection of all roots of that polynomial.
Yeah.
Right. So he's saying if k has less than q roots, that means that at least one root is a multiple root.
Yeah.
Okay. So now it's factored in Lx. Remember that L is a splitting field. So this polynomial is now in Lx, because this alpha is may not be in the base field, but it is in the definitely in the splitting field.
Yeah. It's in there.
Okay. Okay. So now mod of k is less than q. Then we have any two roots to be same. Now we assume that without loss of sanity that alpha 1 is same as alpha 2. Okay. If you have any other reputation, then you can just take it in the beginning, and without loss of sanity, you can consider them as your alpha 1 or alpha 2. Okay. So xq minus x is now x minus alpha square gx. Now you have doubt about this step, that differentiate both sides.
Yeah.
Right? So it's not the analytic differentiation.
Yeah.
Okay. So it's just you are giving a polynomial fx. You can define some other polynomial gx and say that it's the differentiation of fx.
Yeah.
By
So
the use,
basically, yeah, we were defining qx to the power q minus 1 to be the differentiation of x to the power q, right?
yes, x to the power q.
So
yes.
my doubt was that then we would have to prove the product rule to use it.
We have to prove
The product rule to be able to use it.
Yeah, that product rule. See, you have to define it over the axis, and then you can say that extend this linearly.
Yeah.
Right. and then product rule will definitely follow.
It's not clear to me how product rule follows. Can you explain again?
Okay, so I could not write here. Maybe uh, I will share the writing pad and then write there.
Mm.
This will follow same as it follows in the usual definition of
So
differentiation.
the proof should be different, right? Because in that case, we use the epsilon delta definition of limit.
No, no,
And
no. We need not to use epsilon. You just use the constructive argument. Let me just. You can see the screen, right?
yeah, I can see it.
Okay, so just. So you want how say gx fx you have its differentiation is same as gx f prime x plus g prime x fx, right?
Yeah.
So let your gx is summation of ai x raised to I is from 1 to n, and fx is summation of bj's, xj's, j is from 1 to m. Now you have to evaluate LHS and RHS separately.
Yeah,
So
so
it
we
is,
will get it to be equal. Is that
yeah,
idea?
yeah. So then we will get the equality.
Okay, so yeah, okay, that's right. So I have another question. So
You just you use that
yeah. So yeah,
differentiation satisfies this x raised to n. When you differentiate it, you will get n x n minus 1 and alpha, and then you differentiation is a linear map. Okay, so you just need to extend it linearly and then you will get it.
okay. Differentiation is a
See,
linear
because
method.
here you have nth coefficient here.
Yeah,
Maybe
yeah.
we can just try one or two steps and then you will get more idea.
Okay, okay.
So what is gxfx? Gxfs is summation of uh, k equal to 1 to n plus m ck x k, and your ck is uh, a naught bk plus a1 bk minus 1 and so on to ak b naught, or in either way it is just the summation of ai b k minus I is from 0 to k, right?
Yeah, yeah.
So you differentiate this gx fx prime, what it will be? It will be uh, summation x equal to sorry, k equal to 1 to n plus m, ck will be as it is, and then differentiate this x prime k.
Yeah.
But
Yeah,
this is the thing.
I think I get it, the idea.
Okay, so this is ck and then you have k times xk minus 1.
Okay.
Now you evaluate the RHS part also and you will get the same thing.
Okay. So another question I had is, so when we are differentiating x to the power n, we are getting n x to the power n minus 1.
Yes.
But we may not actually have n in the field. So how are we taking that? Are we taking like the unique homomorphism from Z to that field?
No, no.
And
So,
the image of n to be actually n?
see, this means you are adding xn minus 1 n many times.
Okay, okay.
So Couldn't find the point here. This just mean xn minus 1 plus xn minus 1 uh, n many times.
Okay, okay.
Okay. Yeah. And that is definitely in the field because xn minus 1 is in the field.
Yeah, yeah. That's a little bit.
Not just
Okay.
field. It's all happening in the ring of polynomials.
Yeah.
Okay. Hmm.
Okay. Thank you. I get it.
Okay. So the rest part is okay.
Yeah, yeah. The rest part I is okay.
Okay.
Okay. I had one question. So, about the final exam. So there was a system compatibility test, but that was computer based. So uh, we don't have to scan or write anything in script, right? So it will be all.
See, I don't know means anything about it. It's all about the technical team that is going to take care of it. So you can
Okay.
write them directly and they will respond to your queries.
Okay. 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 Thank you.
Because I won't be there in invigilating the or checking your answer sheet anything. It's all up to them.
Okay. Okay.
Yeah.
Thank you.
Okay. So shall I continue with the assignment solution or you have any other doubt?
No, no, I have no more doubt. You can
Okay.
continue. Okay, one last question. So is the recording available of this assignment solutions?
Yes, definitely. You can find them on the site as on the website itself. Let me just share the screen again. So this is course web page, right?
Yeah,
On swim. So here, if you just scroll it at the end, you can see this problem solving session.
yeah.
This. So once you click it, there this new option will be available. You just click it again. It's opening.
Okay, thank you.
So then you will get the link of this Excel sheet. And in this
Yeah,
Excel sheet, like, so there are two sessions going on. One is by me and one is by some other tutor. So you will get the links for recordings and notes for both. So it's just opening. Let me just. Yeah. So this is the first one is by me and the second is by Prakash. Okay.
okay.
This type has all the notes and these are the recordings. Okay.
Thank you very much.
Oh, let me just share the writing pad again. Okay. Yeah. So, so let us continue with the uh, solution of problem one. So we were at the part B. Just erase it from here. So in the part A, we saw that if something is a field extension of Q, if there are two field extension of Q, then for each field homomorphism, uh, the field Q is being fixed. Okay. Now part second says that if K and F are field extension of Q root 2, then Q alpha is equal to alpha for every alpha belongs to Q root 2. But that is not going to be the case because part B. This says so let phi from K to F be a field homomorphism. So what's the situation? So Q has the field extension Q root 2, and there you have two field extensions K and F, and you are defining a map phi between these. So by part A, we know that phi of alpha is equal to alpha for all alpha belongs to Q, right? So it's all about, so we just need to say just need to see where root 2 is mapped by through phi, right? But you have two choices for root 2. So but there are two choices for root 2. This is already discussed in class, because that image of root 2 has to satisfy the minimal polynomial of root 2, and minimal polynomial is of degree 2. So it has only two roots. One is root 2 and minus, other is minus root 2. So it has to satisfy one. So root 2 can be mapped to either root 2 or minus root 2. So this has already been discussed in the class. Okay. So this is namely root 2 and minus of root 2. So it's up to you. So the field homomorphism from F, say phi 1 from F to K, such that so there exists a field homomorphism from phi from F to K, such that root 2 is mapped to minus of root 2. This implies the field Q root 2 is not fixed by phi 1, right? So as this is not fixed by phi 1, so the option is false. So we have the option to be false. Okay, so yes. So the third part says if K is a field of characteristic 11, then f of 11 is contained in K. Okay, so this has already been discussed in the lectures. The C part is this is true since in the lectures we have seen that a field of we have seen that a field of a characteristic P has the property Fp is contained in field, let's say K of characteristic P has the property that Fp is contained in K. So here your P is 11, so there is no issue in that. So the part C is also correct. Now D says if K is a subfield of C, then R is contained in K. So this is also false. Let us just see why. So in the first part, we see that if something is a field extension of Q, then that contains Q. So C is also a field extension of Q. It contains Q, no doubt. But now, uh, does a subfield of C contains R or not? So let us see why this is false. First of all, this is false since since this field Q of I is a subfield of C, but Q of I does not contain R, right? So that's what we were expecting. That's what the question says, that whether it contains R or not. So it doesn't contain it. Not necessarily be true that it contains R. Okay. In fact, something more is true, but let's not go into that. That's related to the degree of field extension, that there is no field in between R and C, because C is a degree to extension. And so if you have a field in between R and C, then either it's going to be R or it's going to be C. You can just check it through the multiplicity result of field extensions. So if a subfield of C that strictly contains R, then that has to be C. Okay. So in that way also you can see that you just need to find a subfield of C which is not containing R, and then you will have the a counter example for this. Anyway, this Q raised to I one such counter example I have precisely given you. So I hope this question is the solution to question 1 is clear. And if that is the case, then we can move to question 2.
இது ரொம்ப சின்னமா இருக்கும் தெரியுதா?
இதுல பாரு, இதுல
Okay, so here is question number 2.
Sharing key and meeting ID sharing வருதா இல்ல? வேணா அதுக்கு என்டர் பண்ணா.
Okay. So it says let K be a field such that the only irreducible polynomial in Ks are the polynomials of degree 1. Then, so this is a specific property that is being given to you for the field K. That so what does this mean? That if you have a polynomial of degree more than 1, then it is always reducible, right? So there is no irreducible polynomial of degree more than greater than 1. So that precisely means that. Okay, so Q denotes the field of rational number and R denotes the field of real numbers. Choose all the correct statement. Now, first thing it says K be a finite field. So, yes, if you have any idea about it, then you can say. Otherwise, I will start solving it. Yes. So there are two ways to argue that. So let us first see the easiest of them. So uh, let K be a finite field. Okay, and K is, as I said, K is nothing but say A1 dot 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 AN. Then consider the polynomial let me just define this polynomial as this fx to be x minus a1 x minus a2 dot 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 x minus an plus 1. Okay, so as this is a field, so clearly you have cardinality of K to be greater than equal to 2, because the field must have size at least 2, at least additive identity and the multiplicative identity should be there distinctly. So you consider this polynomial. Uh, what can you say about the degree of it? Degree of fx is what? This is equal to the cardinality of K, right? Because you are multiplying this linear factor in x n many times, and n is precisely the cardinality of K. Degree of fx is equal to cardinality of K, which is greater than equal to 2, and which is definitely strictly greater than, we can just, so this is greater than equal to 2, right? Now by the assumptions on K, what you can say. So it says let K be a field such that the only irreducible polynomial in Kx are the polynomials of degree 1. So if you have a polynomial in degree greater than equal to 2, then this polynomial has to be reducible by the assumption of K. Fx must be reducible in K, or Fx must have a root in K, right? But if it's easy to see that Fx doesn't have a root in K. Why is it so? Because So this is say 1, but by 1, what you will get, f of ai is nothing but you have the first, this polynomial, this term will be 0 if you just put any of the ai in place of x, because these are linear factors. So ai minus ai will become 0, and thus this part will become 0. So you just have 1. It will be 0 plus 1, which is going to be 1, and that's not 0, right? So uh, this implies that fx does not have a root in fx does not have a root in k. So this is a contradiction. You are expected that it was expected that it must have some root in k by the assumptions over k, but it is not having any root in k. So this implies that k must be a must be an infinite field. So clearly your part 1 is not true. This is false. Okay. Okay. So yeah, second part says k has no finite extensions of degree at least 2. So means it is just omitting the degree 1 extensions. Definitely every field has degree 1 extensions. It is precisely the field itself. But apart from it, it's not having any other finite extension. So this is true, and one has to see why. Okay. So for that, let k be a finite extension of f, right? So of degree greater than equal to 2. Then what can you say? Since it's uh, a extension of degree more than 2, this implies first uh, k set minus f is not empty, right? So let alpha inside k minus f be an element, right? Now you can think of an irreducible polynomial of, so since this is this alpha is outside f, right? So the irreducible polynomial of alpha must be of degree greater than 2. Let alpha belongs to k be an element, then the minimal polynomial of alpha over f must be of degree greater than equal to 3, right? And why this minimal polynomial exists? That's also one question to ask. So minimal polynomial exists since each finite extension is an algebraic extension. So thus alpha must satisfy a polynomial in fx, and then you can choose the polynomial of minimal degree, and that turns out to be a minimal polynomial. So that's why the minimal polynomial exists, and it is of degree greater than equal to 2, because if it is of degree 1, then alpha has to be inside f. But we are not. We are already assuming that alpha is outside f and but inside k. So it has to be degree greater than equal to 2. Now we also know that minimal polynomial are minimal polynomial is irreducible, right? Because if it is reducible, then you will get a polynomial of smaller degree which satisfies alpha, which is satisfied by alpha, and that will contradict the minimality of the minimal polynomial, right? So it has to be irreducible. The minimal polynomial is irreducible over the smaller field, right? In the upper field, definitely it will be reducible because alpha is a root and x minus alpha factor, it will be there, but it should be reducible over the base field, the smaller field. Oh, I think some notation I have. So we in the beginning we were using the notation k for the base field in the question. So I should use different notations. So let maybe L I can take. So let L be the finite extension of f. Oh, sorry, k, and then we need to take an element from L minus k. Right. Need to change this throughout. This is L minus k, and we have a minimum polynomial of alpha over k of degree greater than equal to 2. Then here also it should be from the base field k. Here there is not. So I am just changing the notation. Everything follows similarly. There is nothing to worry about it. So yeah, it's a irreducible polynomial in the base field, that is k. But that contradicts to the assumption that the only irreducible polynomials in k are of degree 1, right? So that was a assumption, but we are getting a polynomial of degree greater than 2, greater than equal to 2, which is irreducible. Thus this is also false. Okay. Now let's move to part 3. It says there exists alpha in k such that alpha 22 minus 31 alpha 13 minus this big expression, this is equal to 0. So yes, what do you think? It is true or not? So don't think too much about this polynomial. Just see that it's a so this just mean that yeah, Muthu, you want to say something?
The negation, if every alpha in K does not satisfy this equation,
Yes.
then this 22nd degree polynomial becomes irreducible over K.
Yes.
So which is the contradiction to the hypothesis.
Yes. Yes. But it might happen that it is a product of irreducible polynomials. Like over R, if you consider this polynomial,
So
x
every
square,
alpha in K is not a root of that equation.
yes,
It's not a root of the degree 22 equation over K.
yes.
So that means
Only thing I'm worried about that what if it's a product of reducible, irreducible polynomials. It might happen that it's a product of degree 11 two degree 11 irreducible polynomials, right? You are on the right track, but just you need to say one more thing. You got my point. What else one has to think that it might happen that it's a product of two irreducible polynomial. It might be a product of uh, two polynomials of degree 11. But that won't happen. Why? Because again, degree 11 polynomial has to be reducible because it's a polynomial of degree greater than 1. Then again, if you break it, then if the polynomial has degree greater than 1, then again you should be able to break it. So ultimately you can say this polynomial degree 22 polynomial must uh, split inside K, right? It should be split. It should splits into linear factors. If it is not, then consider the the factor of degree greater than equal to 1. Sorry, greater than equal to 2. That will create the contradiction to the assumption. Okay. So one thing is yes. So you were right. So C part says so. Before that, it's just a small claim. Then what that one has to check if fx is a polynomial of degree greater than equal to 2 in kx, then fx must split into linear factors in kx. And what is the proof for that? The proof is very simple. So if fx is irreducible, then it's a contradiction to the assumption on K. So fx must be reducing it. Say fx is equal to f1x, f2x. Now it is reducible. Each of them must be either linear factors or reducible. Now, if any of f1x or f2x is of uh, degree greater than equal to 2, then it must be reducible. Right? And continuing like that, we will get fx is some say g1x, g2x, dot 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 g times g degree of f many polynomials, degree of we will get this where each of gi is linear. Gix is a linear polynomial in kx. Okay, and one can definitely argue this using the induction of on the degree as well. So just writing this, one can also use induction on the degree of f degree of f to argue this. Okay, so so the claim is satisfied, right? Now consider the polynomial that is given in the question. Now consider this polynomial. The polynomial is very weird looking expression. So it says alpha 22. So just replace alpha by x, x raised to 22 minus 31 alpha cube minus 24, whatever it is, minus 24 x raised to 13 and then 7. So this was 13, this was 13, this was 7 plus 5 alpha cube alpha 5 minus alpha cube plus 6. Oh, sorry, it should be x. Here also it should be x. x5 minus x cube plus 6, right? So minus x cube plus 6 equal to 0. X raised to 30. Yes. So this polynomial must split into linear factors in Kx, and this implies fx has all roots in Kx. So there is not just one alpha, there should be there are many, right? The roots might be repetitive, but definitely all the roots are in Kx. So this is contradiction to what was the statement. Thus, the statement was false. So there are alphas for which actually you have this, you can satisfy this equation. So, very silly mistake. Fx is not, while defining fx, I should not write it equal to 0. This polynomial is not a 0 polynomial. Yes. Okay. Now let's go to the part D. So it says if K contains Q, then K contains R. So that is what you want to say, Muthu, on this?
If you take K equal to C,
Yes.
the hypothesis will be satisfied.
K equal to C, the hypothesis will be satisfied. Yes.
And C contains Q, but C is not inside R.
Yes. So K, so C is algebraically closed. So each factor there, each polynomial there must, each irreducible factor is of degree 1 only. So C satisfies so, but C contains R. Sorry, it's the other way. It should be C contained in R. Yes, right. So C satisfies the hypothesis of K, and definitely Q is inside C, but C is not inside R. Right. So yes, the statement is false. Okay. And you can also see this in this way that x square plus 1 is a polynomial in Kx, right? So if it contains Q, and then definitely this polynomial x square plus 1, you can consider it as a polynomial over Qx. So it must be reducible inside your K, capital K. So it must contain iota, but uh, iota is not containing, is not there inside R. So that way also you can argue. Okay. So if that is fine, then maybe we can move to the next part. Next question. Let me just write that. Yes. So it says let F3 denote the field containing 13 elements. Choose all the correct statements. First is the polynomial x13 equal to 6 has exactly one root in F13. The polynomial x13 equal to 6 has exactly two roots in F13. So one of them has to be false. Whether one is true or not, that we don't know, but at least one of them should be false. C says the polynomial x cube equal to 1 has exactly one root, and the D part says the polynomial x cube equal to 1 has exactly 3 roots. Yes. So what about x13 equal to 6? How many root you expect that it would have?
There's exactly one root.
What's the reasoning? Don't say that you will put everything in this polynomial and check it's a degree 13 polynomial. It's going to be it's not going to be easy, right? Yes. Can we argue it without like putting without solving this equation?
Anything to do with that cyclotomic polynomial?
Yes.
Cyclotomic polynomial.
So you might be aware of this Fermat's little theorem. Fermat's little theorem. And the proof of this theorem is also like very easy. One can easily see. So what Fermat's little theorem says, if P is a prime number, P is a prime number, prime integer, let's say number has many different meanings. P is a prime integer and A is strictly less than P. Then maybe I think for yeah, then you have less than equal to also, I think you can put. There is no issue in that. So what Fermat's little theorem says, yes. Muthu, do you remember that? So it says AP A raised to P congruent to A modulo P. Okay. So in chat mod PZ, this is the field of 13 element. You can just take this is
So
F30 FP. Yes.
P is prime and A is any integer not divisible by P.
So if it is less than equal to P, then definitely it's not divisible, right?
A equal to P means P is divisible by A.
But A
A is any integer not divisible by P. When A equal to P,
when A equal to P, then also this will follow. What you have when A equal to P, this is nothing but P raised to P minus P. So this is 0 mod P, right?
both of them are divisible by P.
Yes. Right?
Okay. So when A equal to P, the result is obviously true.
Yes, the result is obviously true. That's why some book or some maybe the Fermat also like in his statement might not have said P A equal to P because that is obviously true. So when you are in FP, then what does this mean? In FP, it means AP is equal to A for all A belongs to FP, right? because this modulo part is 0 there. So AP minus A is equal to 0. So that is AP is equal to A for all A in FP. Right? And what does this imply? This implies that only uh, uh, x raised to 13 is equal to 6 in F13 if and only if x is equal to 6. Because if you take 13 power to any other element, then you will get the same element, not 6. So x13 is equal to 6 if and only if x is equal to 6. Clear? So that's why there is exactly one solution to this equation. Okay. Clear? And this Fermat's theorem's proof is also easy, right? You just go in Z mod PZ and you look at the group FP star under the multiplication. Then what is the order of this group? Order of this group is P minus 1, right? Set of all non-zero element is P minus 1. And any A non-zero is inside FP star. So you will get AP is equal to A. Oh, sorry. AP minus 1 is equal to identity, which will implies AP is equal to A. So that is the proof. Right? Separate it. And for P, as we already seen that for P, it will definitely hold. So that's why in the statement of Fermat's little theorem, it is like people don't write A to be P because they want to give this proof. And now for A equal to P, P already divides P raised to P minus P. Okay, so that is what is there. I hope that is fine. Okay. So A is true and B is false. A is true and B is false. Okay, so let us see the part C and D. Yes. What about part C and part D? You cannot use Fermat's theorem here, right? Because we are in F13. If it would have been just F3, then you would have said, okay, in F3 there is exactly one root for this. But you are in F13, you are in a bigger field, so there might be more roots. Yes. So whether it has one root or three root or any, the number of root is
It has
different
three
from that.
roots.
Yes. Why?
1, 3, 9 are the roots.
1, 3, 9 are the root. Good. So, so first of all, one has to say that over a field, each polynomial of degree, say n, degree equal to n, can have at most n roots. This is not the case when you are not in fields, but over fields, you always have this property that each polynomial of degree n has n roots, right? And, like if you say the quaternion ring Q8, there the point this polynomial x4 equal to 1, it has 8 roots. Everything satisfies this, but a Q8 is not a field. So, but when you are in a field, then definitely each polynomial of degree n has at max n root inside the field. Okay, and when you go to the splitting any good splitting field, then in the splitting field you have all n roots. So can have at most n roots. So this clearly implies that x cube equal to 1 can have at most 3 roots in F13. Now, Muthu has already said that, and 1 cube is equal to 1. What was the 6, right? 6 cube, that is equal to
3 cube and 9 cube.
3 cube, 3 cube. Yes, thank you. So 3 cube is 27, which is also like 1 mod 3, 1 mod 13, and 9 cube is 7 to 9, which is also 1 mod 13. So this implies x cube equal to 1 has exactly the roots in F13. There are two, so Muthu, they both of them are cyclotomic polynomials, like x13 equal to 6, x3 equal to 1. But they are behaving differently. So it depends like what the prime power is. So C is not correct, but D is correct. C is false. But D is true. Okay. So I hope this is okay. If that is fine, that maybe we can move to the next question. Okay. So here is question number 4. It says choose all the correct statements. The field, there is a field of order 3125. There is a field of order. So there are 4 orders. So all the required theorems you have. Just quickly tell me what size of the field is permissible.
Any finite field is of order p power n, where n is a positive integer and p is a prime number. Converse also true.
Yes.
That 3125 is equal to 5 raised to the power, so positive integer will come.
Okay. So a field
5 power 6.
So let me just first write the statement that you just said. Any finite field has cardinality p raised to n, where p is a prime and n belongs to n. Also, there exists a field of size p raised to n for each p prime and n belongs to n. So the converse is also true. Okay. So now, yes, Muthu, the first one is a field, yes?
5 raised to the power 6.
Good. So since 3125 is 5 raised to power 6, therefore there exists the field of size 3125. Good. So this statement is true. What about the second?
That 1331 is 11 cubed.
Okay, the C part is also true. So this is true. You are saying part C is also true because 1331. This is 11 cube. Yes. So this is 11 cube. Yes. So therefore,
Sir, hello sir.
yes.
A part வந்து 3125 5 power 5 தானே சார்?
Yes,
5 power
yes,
5.
yes, 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 Nagmani, you are correct. Yes. Thank you. 5 raised to 4 is 6 to 5, and yes, yes, you are correct. Thank you. So there is, yeah. So this is also like there is just a finite, there is just a field of size 1331. So this is also true. What about the other two options?
If you write the prime number decomposition, you are not getting a single prime.
You are not getting a single prime. Yes. Or it is enough to say that there are two primes dividing these orders, right?
Yes.
So B is so 5 divides 4375, and 7 also divides 4375. You need not to find the entire prime decomposition, but this much is also enough. 5 you can directly get because the unit integer is 5. Just check that 7 also divides it. Therefore 4375 is not of the form p raised to n, and which implies there does not exist a field of size 4375. Okay. Same is the case with 1089. There also you can directly see that there are two primes dividing it. 1089. So the sum of integers is divisible by 3. So this is sum of integer is 18. So 3 divides 1089, and you have also had the divisibility rule for 11, that if the sum of alternative integers, this is the difference of this is divisible by 11, then the number is divisible by 11. So here the sum of alternative integer is 9, and here also it is 9. So 9 minus 9 is 0, which is divisible by 11. So it would be divisible by 11. Yes. So
11 is also divisible.
yes. So 11 is also divisible. 11 also divides this. So therefore, there does not exist a field of size 1089. Okay. So let's so these two statements are false. Okay. Let me just move to the next question. Is, there is one more part to this question. Let me paste that also. Here it is. So it says let FPR denote the field of cardinality PR, and then P is a prime, R is a positive integer. PQS denote the distinct prime numbers. Okay, choose all the correct statements. Yes. So, what's your take on the first one?
The result is a field of order P power R contains a field of order P power K if and only if K divides R.
Yes. So we know that a field of order P raised to R contains a field of order P raised to K if and only if K divides R. Okay. Okay. So by this, what can you say about the first part?
1 and Q are the only two numbers dividing Q.
Yes. Okay. So therefore,
Contains
FPQ,
exactly two fields.
yes, contains FP and FPQ only, right, as subfields. So this is correct, right? There are exactly two subfields, including FPQ. What about the second part?
That also contains only two subfields.
FQP contains, yes. But the statement, so the statement is false, right?
Yes.
So FQP contains FQ and FQP only as subfields. So the statement is false. Okay. What about the third part, C?
1QSQS.
Yes. So there are 4.
4.
So C is not correct, but D is correct. FQ, what was, oh, FPQS. It's good that they have already said that Q and S are primes. If they won't be prime, then the situation would have been different. So FPQ contains FP, FPQ, FPS, and FPQS only as subfields. There are precisely 4 subfields, including FPQS, right? So C is true, but D is false. Oh, sorry. C is false and D is true. Okay. So I hope that is also clear. Let's quickly move on to the next question.
Six is exactly same as 5.
Yes, this is exactly same as 5.
I don't know why they have.
They just want to check your counting skills. Class 1 counting skills. They have given one extra question this time. There are 7 questions. They would have like omit this part in question 6. Okay, anyway. So by the same reasoning, F314 has F3, F3 square, F37, and F314 as subfields. So there are exactly 4 subfields, including F314. Yes, so option A is correct, B is false. Okay, and F718 also, like this is, it will have more subfields because it's a product of 2 and 9, not just 2 primes. So F7 raised to 18 has F7, F7 square, F7 cube, F7 6, F7 9, and F7 18 as subfields. Including there are exactly 6 subfields, including F718. So again, even the options are like the same. So A's, C's, false, and D's too. C is false and D is true. Okay. Let's move to the next question. So choose all correct statements. You denote the field of rational numbers. It's on the splitting field. So the degree of the splitting field of x raised to 13 minus 1 over q is 36. So what you want to say over
The
it?
degree of splitting field of the polynomial x power n minus 1 is equal to pi of n, that Euler's pi function.
Always, is it always the case?
X power n minus 1 form.
Over q.
Yes.
At least for prime, I can say yes. It seems not x raised to 6 minus 1 is degree 4, right? What about the x4, x raised to 4 minus 1? Okay, this is
X
just
power 4 minus 1, I
q
minus
eta.
I 1 minus 1.
It will be 2. Let me just take x raised to 6. For x raised to 6, you have x cube minus 1 and x cube plus 1. You can write it like that. So cube root of it has omega as cube root. This is also like again separable, so it is x minus 1 x 1 plus x plus x square, and this is x cube plus 1. So from here you will get omega, and from here you will get x is equal to root of minus 1, cube root of minus 1. So what is Fowler phi function will give here? This will be 6 divided by
Pi of 6.
p minus 1 upon this is 2 by 3. So
One.
this is 2, right?
1, 5, 2.
2.
5
So
of 6 is 2.
so is it 5 q of omega only? I think so. What about this polynomial? This polynomial has root in q, so you can just
Which
x minus 6 minus 1 is you can write it like this in terms of irreducible polynomial, right? X minus 1 has root 1, which is already in q. This has root omega, but this don't has root omega, right?
x cubed plus 1
Yes.
cos 5 plus x 5
X cube plus, it don't have omega as a root, or it will have minus omega probably. Yes, yes, yes. It will have minus of omega as a root, because minus omega cube is nothing but minus of omega cube. Omega cube is 1. This is minus 1 plus 1. Yes. This is q omega. But I need to check whether this is true for any n. At
any
least for prime. So you have already checked.
for any n, if it is the polynomial is of the form x power n minus 1.
Okay. So it was discussed in class, or I don't think so. Okay, but here we only need that for prime, whether it's okay, true or not. Maybe through the idea of splitting field, yes, you can get. You just extend, get the prime extensions, and then probably. But yeah,
In the class he has given us a fact.
in class it was given as a fact.
Yes.
Okay. Then, but I think the proof is also you can like just take prime extensions and try to find a splitting field. But yeah, I cannot rigorously write the proof at this moment. Yeah, if you are saying it is there in the class, then it should be like true. Okay, but we just need for this question we just need the idea for primes, and for that definitely we have already seen the proof here also in the sessions. So we have already seen in previous sessions that this polynomial xp minus 1 has is it non-trivial. Okay. If alpha is the non-trivial, root of xp minus 1, then q of alpha has degree p minus 1 over q. Also this alpha is the primitive root, right? Also alpha is the primitive is one of the primitive root. Means one of the primitive root if primitive pth root if alpha is not equal to 1. So thus q of alpha contains all the roots of
primitive roots of 1.
primitive pth root, right?
Primitive roots of unity.
Yes, primitive root of unity. You want me to write that also? Pth root of unity. That is clear, right? So thus q alpha contains all the roots of x raised to p minus 1. And it is the smallest field containing q and alpha. This implies that q alpha is the splitting field of xp minus 1, right? And this splitting field has a degree p minus 1. Thus your option A and option A is correct. Okay, so this implies A is correct and B is not, because B has, it should be 66 but it is saying 67. So A is correct but B is not. So Nagmani, you are getting it? We have already seen that this extension has degree p minus 1. Yes. So do you have any doubt in that?
7th one. 7th one.
Yes, 7th one. Oh,
3rd and 4th one. Explain, sir. Brief.
3rd and
4th one.
okay, that I will do. That I will do. So, but I am just asking that we have seen in the last sessions that this polynomial has degree p minus 1 over q using Eisenstein criteria. I think you were not there in that lecture, so that is clear to you. That is fine. Why this polynomial has degree p minus 1 over q? Maybe just I will just give us brief idea and then I will move to part 3rd and 4th. So this is like x minus 1 and 1 plus x plus dot 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 x p minus 1. So this polynomial is already there inside qx. So this is not going to play the role, but this is going to play the role. We have to see whether this is irreducible or not. So, and if say alpha is not equal to 1, then alpha will satisfy this polynomial, right? So this polynomial becomes the so this polynomial is satisfied by alpha. So now you have to check whether this is reducible or irreducible over q. So for that, you just take this polynomial as this plus xp minus 1. This is xp minus 1 divided by x minus 1. Then we showed in the in that lecture that fx is irreducible over q if and only if fx plus alpha is irreducible over q for all alpha in q, right? So if you take your alpha to be 1, then fx is reducible if and only if fx plus 1 is reducible. Right? And
We can take alpha equal to 1.
yeah, so for alpha to be 1, this is just x plus 1, p minus 1 divided by x, right? Just replace x by x plus 1. And then using binomial expansion, you expand it. This will be nothing but xp minus 1 plus p minus 1 c1 x p minus 2 dot dot dot. You have p minus 1 x, and then you will have plus 1 minus 1. Minus 1 is coming from this here. This plus 1 and minus 1 will be cancelled out. And yeah, there is some mistake. So this polynomial was x raised to p minus 1, right? Here it is x raised to p, not p minus 1. Here also, like, it will be p, it will be, yeah, pc1, then you have here p, like, and here in the denominator you already have x, so this polynomial will become x raised to p minus 1 plus pc1, sorry, x raised to p minus 2. What? This is p, this is p minus 1. So this will be x raised to p minus 1 after dividing, and you have pc1 xp minus 2, pc2 xp minus 3 dot 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 dot. At the end you will have p raised to x. Now you apply Einstein criteria. All these are divisible by p, and this coefficient of xp minus 1 is not divisible by p, and the coefficient of this, so after dividing x, this will become p. So here the constant coefficient is not divisible by p square. So this will satisfy Einstein criteria that this polynomial is reducible, and so fx plus 1 is irreducible, which will imply fx is irreducible, and fx was 1 plus x plus p, xp minus 1. So this becomes irreducible. Okay, that's why the degree is p minus 1. Clear? Okay, so that's a very important fact. That's why I just repeated it. I will erase it later, no problem. So let us first quickly discuss part C and part D also. Part C says the degree of the splitting field x cube minus 2x square plus 3x minus 6 over q is greater than or equal to 3. Yes, Muthu, what you want to say about it?
That cubic equation.
The root that does not belong to over Q, sir.
Yeah.
The two roots are does not belongs to over Q.
Yeah, so two of the roots are not there. So but you can write fx as x minus 2 x cube x square plus 3. So you can check that 2 satisfies this polynomial, right? So this is 8 minus 8, 0 plus 6 minus 6. So that is 0 once you put x equal to 2. So x minus 2 is a factor. Then you divide this polynomial by x minus 2. You will get x square plus 3. So fx is x minus 2, x square plus 3. Now, so the degree of, so this 2 is already there inside your Q. So that is not going to play any role in the determining the degree of the splitting field. That right? So degree of splitting field of fx is equal to degree of splitting field of x square plus 3, right? But x square plus 3 is irreducible over q, right? It has no roots, as you said that both the roots are outside q. So then what can you say? What is the degree of this polynomial over q? Thus, the degree of x of this splitting field of x square plus 3 is equal to 2, and that implies the degree of splitting field of, because once you have a irreducible polynomial, then the degree is same as the degree of the polynomial. Degree of splitting field of fx over q is 2. So it's not 3, it's 2. That's why the option is false. The polynomial is of degree 3, but the splitting field has smaller degree because one of the root is there inside the field itself. In general, the degree is less than equal to the n factorial, where n is the root of the n is the degree of the polynomial. But here it is very smaller than n factorial. N factorial is 6. In fact, we are getting it less than n. Okay, so it says it's greater than or equal to 3, so the option is false. This is false. Okay, so the last question of this session and also last question of this course, the last part. So what does it say? The degree of the splitting field of x4 plus 1 over q is 4. That many times we have seen already. Any one of you want to say something? That's already been discussed in the lecture notes. We have also seen this.
The splitting field of this polynomial is q of root 2 comma I.
Yes. The splitting field of x4 plus 1 is q of I root 2, and it has degree 4 over q. Yes, so you just need to use the tower. I'm not going to say this again, but as we have seen this question, I think 3 to 4 times in the lecture and in the session also. So but I can just construct that field of towers, the tower of fields, sorry, for you. So you can just, so this is qi, this is q. And then you can say that this has, it has degree 2, and this also has degree equal to 2. Thus the total degree is 4. So this statement is true. Yes. So with this, I'm done. If you have any doubt, then you can ask.
only problem is we should know the shortcut method for any particular problem, because we cannot solve like this what you have done in the exam.
Which part? I think today's
For
questions were
any
shorter.
problem for that matter, if we start solving like what you are doing, so it is difficult for to complete. You see, for 2 hours, you have taken to solve 7 problems.
See, but I was like intended to like explain already known facts also. Maybe
Okay, maybe two times 14 problems, or 3 times 21 problems. What about the remaining problems?
so how many problems you are going to solve? Means,
How
they-
many
they-
problems? Because each question carries 4 marks.
yes. I think so. You are talking about this NPTEL exam.
Yes, it is.
I think most of the things would be like you can solve them without like putting much efforts. If you have followed the lecture notes and discussions precisely, then there won't be any much difficulty. You see, uh, before discussion, before this live interaction session also, if you have followed the notes, then I don't think you need more than half an hour to solve these 7 problems.
Half an hour to solve 7 problems.
Yeah, if you already seen the notes, lecture notes. See, this let's quickly go back, go to the questions. So you need to read this question, and you already know that any field extension fixes Q, right?
Normally, in the assignments, problems are different from what they have discussed in the lecture.
That is
Mostly.
the case.
And then in the examination, it is entirely different.
But see, I
Can
don't
you,
know
okay,
about this
okay, let us see.
NPTEL exam, but
Yes.
I can tell you one thing that generally in what in the courses for NPTEL or anything else, the assignments are a bit tougher than the exam, final exam. Because for assignment, you get a lot of time to think and you have a lot of resources to get the help. But generally, in exam, the questions are easier than assignments.
Let us see.
But this is means I'm just saying the natural phenomena that happens. I don't know what will be there. So it's tomorrow or when?
Sunday, day after tomorrow.
Day after tomorrow. Okay. So I can tell you one thing, that if you have seen the lecture notes and if you have followed the assignment problems, then you won't be very sad after looking at the exam. You would be happy to that you will be doing at least I think 70% problems. That what I feel. I haven't seen the exam paper, but
No, nobody knows.
nobody knows.
Okay, anyway,
Right.
thank you very much.
Okay.
I appreciate your board work. It is
Thank
very
you.
neat.
I don't know which course I will take next time, but yeah, I will definitely take one course related to algebra, but up to them. Okay.
So systematic.
Thank you. Means like it's due to thanks to COVID, I will say. Most of the things are happening online, so one has to like present online and discuss online. So now it's been in the habit. Okay, for anything else, you can like just write to me. You have my mail ID. I already given it in the first lecture. And
Okay, thank
okay
you.
then. Okay. Thank you, Muthu. You are very consistent. So at least I got one partner to discuss or someone to tell the solution. So thank you for that. Okay.
Okay, see you. Bye.
Okay. See you. Bye.